Okay, guys, today then this is not new for us, right? We learned this in high school and just to derive the expressions for the equivalent capacitance of a circuit that has capacitors in parallel and for a circuit that has capacitors in series. Learned this in high school, and this is so important because this is one of the major techniques to solve for unknown in circuits. So every time you have a circuit, sometimes you are interested in finding like the current, like going through like a component or the voltage over that component, and can be very complex. Of course, this is a very easy circuit that you are seeing on your screen, but sometimes the circuits are not so simple. They are very complex. In this, when the circuits are very complex, one very powerful technique to find like the for example the total current in the circuit and the total voltage and so on, and over each component is to reduce this circuit to what we call like a equivalent circuit. And for that we have to calculate, right, for example, what we call like equivalent capacitance, and we are going to see later the equivalent resistance as well. Today we are going to cover the equivalent capacitance for these very simple cases, but very important, very significant cases. So let's start with a circuit that has capacitors in parallel. For these kind of circuits, like you can see here, right? So you have three capacitors that are subjected to a voltage V, and every one of these capacitors, right? The capacitor 3, the capacitor 2, and the capacitor 1, they are subjected to the same difference potential, the same voltage here, right? V. They're exactly the same. So this is a particular characteristic of a circuit when you have elements in parallel. So we can write here that dun, 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 we can write, of course, this element here, the battery, this battery here is going to supply like a charge, and this charge is going to be actually divided by all these three components here. That means that the total charge of this in this circuit here, the total charge applied by the source is going to be just the sum the individual charges of every single capacitor. I'm calling Q1, 2, and I'm going to call this 1. I'm going to use, of course, the equations that we know that this connect is that links the charge on the capacitor with its capacitance. And we know that is Q equals C times voltage. I can substitute, right? I can use this equation too for every single one these charges here, the equation, and I can rewrite, right, the first equation as Q equals C 1 B Q1 plus C. We know that these voltages are all the same. Every single capacitor in the parallel circuit is going to be subjected to the same voltage. So all these voltages here that I circle in red are going to be, they're all V, right? And you can rewrite this, then you can put in evidence this. So you have V C1 C2. I can divide this. What you have here, you have Q over V going to be the sum of these capacitances. Nice help. Okay, and this one here, this term, the right hand side here, this is going to be the equivalent capacitance. We can generalize this. Of course, you can always, if this is valid for 3 or 2 capacitors, this is valid for any number of capacitors, then we can generalize. Let me put in, can generalize we can generalize that equivalent capacitance as when you have capacitors in parallel, you just have to sum up summation on I 1 n of every single capacitance of each individual capacitor in the. So for a parallel, when capacitors are in parallel, so we just, all you have to do, find this circuit here, right? It's simpler than the previous circuit here. All you have to do is just to add, just to sum all the individual capacitances of the each capacitor. Okay, so what brings us to the next case is how we find the equivalent capacitance for a circuit in series. Hey guys, remember, just as a reminder again, we are trying to simplify. We are trying to from this circuit that is a little bit more complicated, right? To simplify this to this kind of circuit, and they are equivalent. And this is a very powerful technique to find unknowns in a circuit. So it's the first one that we're going to learn. Okay, so let's go how you do that. We know that the total voltage, I have the battery here, is supplying like a voltage V to this circuit. The total voltage is going to be the individual sums here of every single, the voltages over every single capacitor. Have that this V sum of V1 plus 2, 3. And again, well, from the equation, capacitor equation, right? Know that the voltage is going to be, actually this is the same equation. I'm just rearranging equation definition of the capacitance, right? And just rearrange. I know that the Q divided by the capacitance. I got everyone. I'm going to use the equation. I'm just going to substitute, right, to rewrite the equation 3 in terms of this equation 4. So it's going to give me B, but these components, these capacitors are in series. That means that these all three, the charge is the same, right? And we can call them Q, just Q. The index is going to be Q. You can put this in evidence. I'm going to have those. And here one, one. You can divide the equation by Q. But I'm going to write this. Term here. And this, the inverse of this one, guys, of this term here, if you look at this, the left hand side, this is 1 over, is the inverse, right? So if you just elevate the whole equation minus 1, just in 1, so you're going to have capacitance. That means that this term here, we write these terms here as okay, and then similarly, what we did in the first case here, we can actually can write this, can generalize this for any number of capacitors in series equivalent capacitance. Then in this station of for the capacitance. So this is for capacitors in series. Just first one parallel. I would like to finish this part. Okay guys, we are going to the next one. Page. Back this line.